Okay. Directional derivatives and gradients. Last time we left off, we came up with these formulas, or something similar to this, where we have the gradient is defined to be a vector of partial derivatives, and the directional derivative is the gradient dotted with some unit vector, where unit vector is some direction that we're trying to get to. So what I wanted to do is let's go for a hike. Yeah. Okay.
What is that original?
So I want to go on a mountain somewhere in Colorado, probably. And this is the default function in the plotter. So this looks good enough to hike on. Okay. So let's go for a hike on this mountain. And I think it might be good to have a map or a compass, right? So let's take a picture of this. And let's take a picture of our map. And we might as well take a picture of our function. So let's work with this function. It's 7xy divided by e to the x squared plus y squared. So this is how our function would look like, our graph. So let's put ourselves somewhere in the mountain. Where should we be? Should we be all the way on top? Let's not be all the way on top. Let's be, what? Halfway down. So let's put ourselves over here maybe. It looks like this is a measure of 2. So I'd probably go maybe 1.5. I'm start playing with some numbers that aren't very nice. But maybe we are at x is equal to 1.5 and y is equal to 1.5. So we're here on the mountain, and my map tells me that I'm here on my xy plane. Okay? Now, standing on this mountain, I'm on this spot. I can ask myself a couple of questions, like if I move along the x-axis, I guess I should say this is my map. This is north, south, east, and west. So if I move east from where I'm standing, am I going to feel an increase or decrease in height? It looks like I'm going to feel a decrease in height, right? So more specifically, how is my height going to change when I start moving east? Yeah, so that's the decrease part. So what is my change in height? So that could be one question. Change in height. Actually, maybe let's call it rate. of change in height going east. So going east is equivalent to taking the derivative with respect to x. You're moving along the x, right? So to answer that question, the answer is it would just be the partial derivative with respect to x evaluated at 1.5, comma 1.5. Okay? Suppose we should actually figure out, since we have a function, we are on a point and stuff. So let's figure it out. So we need our partial derivative. Let's just call it z sub x is equal to, oh man. Oh, so let me rewrite your z function as 7xy times e to the negative x squared plus y squared. We could, but since we have the tools for getting the exact values here, and the exercise is to find the gradients and directional derivatives, we should just do it like this. Yeah. Why is it negative? Well, I don't know if it's negative. I hope it's negative. If this is oriented the way it looks like, where x positive and y positive point out this way, then it looks like I would, if I go x positive, I would be going down this way. So hopefully it'll be negative. So the derivative of this with respect to x is 7x is a variable, so 7y is a constant. This derivative of the first times the second. Should maybe figured out a nicer function. The first, which is 7xy, times the derivative of the second, which is e to the minus x squared plus y squared, times the derivative of the numerator, which is, with respect to x, negative 2x. I suppose we should try to simplify this. Normally I wouldn't care about simplifying derivatives, but if we're going to plug in numbers and do stuff with it, it might be good to simplify. So it looks like I can get a 7y out, and e to the negative x squared plus y squared. So I can factor that out, and then I would just have 1, and then the 7 is gone, negative 2x squared, yeah. Right? So if I put in that point 1.5, 1.5, I should get a negative number. Okay, can you guys do that for me, or? Let's get a couple people to do it, and then we'll confirm. Since there looks like there's symmetry in the variables, if I take the derivative with respect to y, I'll probably get the same thing, right? Except the x's and y's are switched. You guys get it? Okay. Negative, what is it? 0.408. All right, so we got a negative number, which according to the graph we should have gotten, and so it looks like it's good. And if we move along the y-axis, or according to the compass, if we move north, we should get the same thing. If we calculate z sub y, it looks like it should be pretty close to this. And then we put 1.5 in, and we're going to get something else. Yeah? If we set it equal to 0? What do you mean?
If you set the function charter should get the same.
Maybe. Not necessarily. Setting the derivatives equal to 0 is, what does that sound like? Critical points, yeah, critical numbers. And what do we do with critical numbers in calc? What was the application for that? So we're trying to maximize and minimize. So we will do that, but not today. So the whole idea of maximizing and minimizing in calculus is a really big deal topic. And so there's going to be an extension to the optimization that we used to do back in Calc 1. Yeah, but we're not going to do that yet. All right, so the rate of change in x and the rate of change in y would probably be the same thing. So I'm not going to bother with what happens if we go north, because it should be the same what happens when we go east. So let's do something else. We can go west or south, right? And if we go west or south, we'll probably feel the same thing, except instead of going downward, we'd have to climb up. Okay? So let's do something more interesting and actually make use of our directional derivative formula. What if we go a different direction that's not north, south, east, or west? No. Let's use a compass. North, south, east, west. Which way? Southwest. Let's go southwest. Okay. So what we want to do, according to the formula, the directional derivative formula here is we want the direction of u. And remember, last time we made a big deal about u being a unit vector. So it looks like we need to find out what u is equal to. So let's figure out what u is equal to. U. This is u. So rate of change in the u direction. So what is u equal to? Too many arrows. What's u equal to? Would it help if I take u and put it in standard position? Whoa, that's just a tip. What's u equal to? No, seriously. This isn't a trick question. Just tell me. What? -1, -1. Okay? So -1, -1 isn't quite u. Why is it not quite u? We have to make it into a unit vector. So that's the only thing. But the direction is there. That's what, that's the first step. We want that direction. So u, if we find the magnitude of this, should be square root of 2, right? So the u vector that we're looking at is -1 root 2, -1 root 2. So that's the direction that we want. And according to the formula, we're going to take the gradient And we want to evaluate it at the points 1.5, 1.5. And then we're going to dot it with U. And that should tell us how we're going to change our change in height as we move along the U. Okay? So what's our gradient? Our gradient looks like it's a big mess over there. So the directional derivative of the function in the direction of U, and then at 1.5 comma 1.5 is equal to the gradient of the function evaluated at 1.5 comma 1.5 dotted with the U vector that we just found. So what I need to do is I need to figure out what the gradient is at 1.5, 1.5. So we need to figure out what happens when we put 1.5 comma 1.5 into fx. Oh, we already know that, right? That's this thing. And then we want to know what happens if we put 1.5 comma 1.5 into fy. And we said it was going to be the same thing, but I'm going to double check with Mathematica just in case. And then we're going to dot that with U. So let's see. So that's the gradient, and then I want to evaluate that when x is 1.5 and y is 1.5. And so I do get the same numbers. So negative 0.408 comma negative 0.408. And then I'm going to dot that with negative 1/2 or 1 root 2, negative 1 root 2. So it's just a simple dot product, it looks like. And it looks like I get 0.577. Which, according to this map, tells me that I would be going up. So it's positive. It's a good thing I got positive because that's what I should have been expecting. And if I move in this direction, I would be, my height would be changing going up. So that would be a hike of a 57% grade. Pretty steep. Yeah. Okay? So that's what directional derivatives are good for, or one of the things that they're good for. It helps you find the rate of change of something, and we use the gradient, so that's an important use of a gradient, finding directional derivatives. Are there any questions about this? Yeah.
So what was the negative 0.408? Is that a rate of change?
Negative 0.408 is the change if I go in the x direction. Negative 0.408, this one is a change in when I go in the y direction. And put together, that's a vector. Now, put together as a vector, it's going to be meaningful yet. There's going to be some meaning to this that we'll uncover a little bit later on. Yeah.
So if you go northeast, same mean vector, or you can be positive.
If I go northeast, yeah, I'd be going this way. And then it looks like I'd be going down, so it should be the opposite sign. I guess a more interesting one is, what if you're not going northeast? What if you're going at a different angle? So as long as you can give me a vector to see where you want the direction to point, and then we can figure out what your rate of change is when you go in that direction. Okay? Yeah.
So I think what's weird is the arrow you drew for going southwest.
Uh-huh.
So is that pointing southwest?
I think, you mean on this surface? I hope so, because this is your N, this is your north, like positive y is north. And this is east, positive x is east. So north, east, and then this is south and west. Whoa. West. Okay. All right, are we good with the mountains and maps and hiking and rate of change in height? That doesn't look convincing. Is there a question that you can ask if it's not quite clear? For those people who gave me these faces. If we don't have a question, we're going to take it up a notch. I don't know if anybody remembers that. Kick it up a notch is really what. All right, are you ready?
Yeah.
Let's go.
Yeah.
All right, so let me think out loud like I'm making your exam problem. And here's the scenario. I want to create a really cool problem that translates to hard. I want to create a really cool problem that does a three-dimensional gradient and three-dimensional directional derivative problem. Okay. So what I'm going to imagine is, first of all, I need to come up with a three-dimensional function. And then after coming up with three-dimensional, I guess more of a scenario, a three-dimensional scenario, and a function scenario, and then I'll start coming up with problems. So let's imagine, first of all, let me lay out the piece of information that might be important here. So and if you have a function that now takes 3 dimensions for an input and then outputs another value, a 4th dimension, then this is how your gradient would look like. So of course you'll have 3 components this time. And then your directional derivative would still be the same formula, except it'll be in 3 dimensions. So I'll still write the same way. Except the gradient of f will have 3 components, as you see up here, and then the u should also have 3 components. Okay, so that's the background work. Now let's think about a scenario. So imagine we're in a room, and let's say there's a heater somewhere. A heater usually, I don't know where the heater would be, but let's just, to make it really simple, we can either have the heater right in the middle of the room or in a corner where it gives off heat. So let's put it in the corner. So this is your room, and this is your heater. Okay, so the x, y, z will describe your space in your room, where 0, 0, 0 would be that corner where the heater is. Now I need to define the function. What's the function? So the function W, a common use or a common application for something like this would be W would be a temperature. So instead of calling it W, maybe I'll call it T. And the thing about the temperature is that the temperature is different at different parts of the room until it heats up everything and everything's about the same. But if the heater's on, you move closer to the heater, it's a little bit warmer than if you're farther away from the heater, right? So now I want to create a function that gives me a larger value the closer I am to the origin and gives me less of a larger value as I move away from the origin. Okay, so I'll say T is equal to, I'll say T of x, y, z is equal to, let's say, e to the negative x squared plus y squared plus z squared. Maybe I need to, I'm making this up, so could be some things that will change. I think I need to multiply this by a number. So if I'm right at 0, 0, 0, this is just e to the 0, which is 1, right? And so how hot is the heater? What? 72. And we can decide whether this is Fahrenheit or Celsius. Well, maybe it's a heater for a room where there's no people in there. I don't know. Maybe it's a heat source in the physics room. They have the whatever. All right. So we have a function, we have a scenario, and this kind of makes sense a little bit. A little bit makes sense, where if I was right there at the heater, I'd be at 72 degrees, and then if I move away from the heater, let's say 1 unit away, this is e to the negative 3 power, 3, 1, 1, 1. So e to the negative 3 is less than 1, I think, times 72, so it'll shrink down. So the farther I get, the farther away I am from the heater, the less the temperature is going to get. Okay? So is the scenario good? All right. So now let's find an activity that's happening in this room that's going to force me to have to try to calculate a rate of change in temperature. Okay? So some ice that you want to say ice? It has to be things that are moving so that we move from one thing to another. And it should be in space. So for people, we're just kind of walking around, right? And so that's not going to be helpful. So we need something that's flying. So like a fly. So let's say there's a fly. So a fly is buzzing around, and we can give it a path, or we can just give it a position. So let's just give it a position for now. Where is the fly in space? And this is in the first octant, so all x, y's, and c's have to be positive. So let's say there's a fly flying around. Where's the fly? So there's a fly in the room at 12, 14, 30. Okay? And the fly is moving. they have these like quick line things, right? So at that instant, at that point, it has a specific temperature. It's going to move in a particular direction, so I need a direction that the fly is going to move to. What? 1, 2, 3. So a fly is flying around. It's moving in a direction of 1, 2, 3. And the question is, what is the rate of change? So what's the rate of change in temperature that the fly is going to experience from the point 12, 14, 30, and as it moves in the direction 1, 2, 3? So that's the question. Yeah. So we're looking at the directional derivative at this point going in the direction of u, where u is a unit vector. Okay? So it looks like we need some partial derivatives. We need to make this v into a unit vector u, and then we need to dot that. We need to evaluate it at 12, 14, 30, and then evaluate. Okay, that's easy enough. Is it easy enough? All right, so I'm going to call my function Do I need to do it? I mean, we got the thing. Yeah, okay. 72 times e to the x squared. Oh, yeah, negative. Oh, I got to do a bunch of things. Plus y squared plus z. So the gradient, again, this is one of those nice functions where it looks like it's symmetric. So to take the derivative with respect to x and try to figure that out, derivative with respect to y and z should look very much the same, except for some different things swapped around. So looks like this is going to be my gradient. I got 144. And then the e to the x squared, e to the negative x squared plus y squared plus z squared can get factored out. And then it looks like I just have x, y, z. I suppose I should put that in the notes, huh? So first I want the gradient. This is the gradient that I got. This is grad f. And I can actually simplify this a little bit, like I was saying, and that's to take out the negative 144 and then the e to the negative x squared plus y squared plus z squared. So if I take that out, all I have left is an x and the x component, a y and a y component, and a z and a z component. Okay? So Yeah, I guess the partial derivative of this thing with respect to x is 72 is a constant, e to the same power, times the derivative of this with respect to x, which is negative 2x. And so the 2 times 72, I guess, is 144. All right, we want to evaluate this at the point where x is equal to 12, y is equal to 14, and z is equal to 30. And then so let's do that real quick. Y is equal to 14 and z is equal to 30. Yeah. Yeah. All right. It gets cold fast in this room. Whatever. Negative 144. Did you guys figure out what 12 squared, 14 squared? I guess I did that. Yeah, 1240. So that's my gradient evaluated at that specific point. Now I want to get a unit vector out of this v. And so it's really just 1, 2, 3 divided by the magnitude. So 1, 4, 9, 14. I guess I should have just taken this outside. So the actual unit vector is 1 over root 14, 1, 2, 3. And then that's it. We just need to dot them. So the directional derivative, du of f, or I guess I should have been using t the whole time, but oh well, is equal to negative 144 e to the negative 1240 dotted with 12, or times 12, 14, 30, dotted with 1 over square root of 14, 1, 2, 3. So the constants are just constants. I can bring all that stuff out together. So I get negative 144, not the constants, the scalars, e to the negative 1240 divided by root 14. And then the dot product of this, 12 times 1 is 12, 14 times 2 is 28, and 30 times 3 is 90. And so whatever this turns out to be is a number. This is 130. So now multiply by 144, and then you're all done. Okay? Yeah?
It's like the only source.
Yeah, that's the only source of temperature.
I was trying to imagine.
Well, yeah. Imagine a mystery lab somewhere in the CIA where they have this heating thing in the corner, and then they put some mutant flies in there, and then they can survive extreme temperatures. Okay. So if we include like windows and different sources of heat and cool, then our function could get a lot more complicated. I thought about, having a couple of windows open so there might be a sine wave along the x or something like that. And then, no, Pat doesn't like that idea. But yeah, that's how things can get complicated. With different other heating sources or cooling sources in the room, then your function just gets more complicated. Okay. All right. Well, that was fun. Yeah.
I have a question about this annotation.
Uh-huh.
That it's just
Directional derivative. The u is the direction that it's going, and the f is the function. So really, this came from the function that we're using is actually t, so it would have been more appropriate to use t. And the direction vector that was first introduced was v, but the thing is that v is not a unit vector, so we changed it to u. But in terms of what's given, our given temperature function is t, and our given direction vector is v. So it's going to be like the same thing. Yeah.
Are we always going to be given, or in this case, for these type of problems, be given the direction, or do we have to find?
You might have to find the direction. Like, let's say the B is at 12, 14, 30, and then the B wants to go where the food is at 0, 5, 7. So you have to find a direction that goes from one point to the other point. Aaron?
If you didn't change it to a unit vector, what would that say?
What would happen there is that, according to our formula, the rise over run wouldn't be your exact rate of change anymore.
Would it be the average? Or that span of the vector?
Maybe, I don't know.
I don't know.
It could be. Let's just say that would be wrong, and then don't do it like that. Okay, so the way we derived it yesterday, we forced it to make it look like a unit vector for the rise over run so that we can get the exact slope. And so if we made the run go longer, then you wouldn't get the exact slope anymore. All right? Okay. Let's do something else fun. I am. Yeah, I don't know. I don't like line paper. What are we going to do now? Let's go back to 2 dimensions. Yeah, I don't know if this is going to fly with you guys, but let's see. Let's go back to 2 dimensions where we have. Oh, I know what. I can always do my fallback surface. Oh, we need to get rid of that page. All right, let's go back to the surface. And some point on the surface. And this time, we cut it with a plane parallel to the x, we cut it with a plane parallel to the y, and then we cut it with another plane that's pretty much perpendicular to the xy plane. But now let's do something that we did before, and that is to cut it with a plane that's parallel to the xy plane. Okay, so just a question: what what plane am I using so that I cut this surface and I intersect that point? Can you give me an equation for the plane that I'm using to cut to get that point? Z is equal to what? Z is equal to, I think we can get more specific than K. What? F of x naught, y naught. Also known, I think, as we called it before, Z naught. And so when you put x naught, y naught, which is a specific constant point, or constant value, constant point, when you put that into the function, we're going to get another constant. So z is equal to k was correct, but to be more precise, z is equal to z naught, or z is equal to f of x naught, y naught, because f of x naught, y naught is a constant. Okay? But you can call it k if you want. So, what do we have here? Z is equal to k. No, wait, that's a plane. So, I guess my question is, we could take a look at this value over here, or not value, but this curve. Z is equal to k, we would call it. What is this called again? What? Level curve. Or contour. So this is a level curve. This is one particular level curve that is cutting the surface at that point, right? So let's take a look at that level curve flat on the xy plane. Oops. Okay. Now this is a level curve, right? Let's parameterize this level curve. Let's parameterize the level curve using parametric equations. R of t is equal to something with an x of t, y of t. And since this is some abstract function, representation, general, arbitrary, we don't quite know what it is. So let's just say it's x of t, y of t. It could be sine and cosine if it's a circle, or it could be an ellipse, or it could be a parabola. We don't know. But we can parameterize it. Okay? So this is kind of a silly thought, but what happens if we take that curve and we project it back up on the surface? We get the line of the curve of intersection. We get this curve right up here, except it's now up on the surface. Right? Is that making sense? So I'm going to make up another variable r. Let's say geez, I run out of letters so quickly. Greek letter. S. Yeah, I used S last time, I think, but it was kind of weird using an S. But I think if I put an arrow on top, it'll be okay. So S will have the same x and y values, but my z value, do you remember how we did the z value last time when we projected something up on the surface? Z of x of t, y of t. So in this case, I'll call it f of x of t, y of t. Right? Or you can even think about it as f of r of t. Because r of t is x of t, y of t, and that's just a vector or point that goes into the x, y components. Okay so far? So now I'm up here, right? And this is what I have so far. I'm kind of interested in taking the derivative for some reason. Let's take the derivative. So let's take s prime of t and see what happens. Okay, the first two components are kind of boring. I'll just take the derivative of that. Now I need to take the derivative of f of r of t. It looks like a chain rule, right? It's the partial of f with respect to x times x of t. It's partial of f with respect to x times x prime of t plus partial of y times y prime of t. That kind of looks like a it kind of looks like a dot product, doesn't it? Hey, what's the first one? Hey. What's the first one look like?
The gradient.
It looks like the gradient, doesn't it? And this is just, well, if we put it back in terms of r, it's just r prime. Getting kind of nervous here. That looks kind of lame. Wait, does it look interesting? Maybe it does look interesting, huh? So the gradient dotted with the derivative, I mean, the r prime is you know, depending on which direction we parameterize, it's really just a tangent vector to the curve. And the gradient, well, we don't know what the gradient is yet, but we'll figure it out in a minute. But the z component is a dot product of these two things. Are you with me? Are you guys like on the edge of your seats? F of r of t. Let's go back to f of r of t. This is x, y, f of r of t, right? That's this curve right here. It has the same x and y components. And then the z component is f of r of t. What can you tell me about f of r of t? It's a z component. Give me more. It's what? It's the height. Some more? I want to put something next to this equal sign, and there's three possible things according to the picture that we're seeing up on the screen right now. What can it possibly equal to? Think. Give it to me. No? What can it equal to? And there's three things on the screen right now that it could possibly equal to. What? K. It could be equal to K. It could be equal to Z naught. It could be equal to f of x naught, y naught. But the point is, it's equal to a constant. Right? 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 The height, somebody said height. Maria said height. That's the f of r of t is the height. Does the height ever change here? No. Why? Because it's constant. Because we cut it with a plane, right? That's how we got it to begin with. We cut it with a plane, and we found the parameterization for that 2 dimensions, and then we put it back up. When we put it back up, it's still going to be in the same place. It's going to be on this plane, and it's not going to change in height. Yeah, that's a level curve. That's what a level curve is. We took the level curve down, we put the level curve up, and we shook it all around. And then we found that it was constant. Wait, what did we do? We took the derivative of that. What's the derivative of a constant? So the dot product of a gradient and a tangent vector is 0. And that means they're perpendicular to each other. The dot product of the gradient and a tangent vector is equal to 0. That means the gradient and the tangent vector are perpendicular. And since we did this for an arbitrary function, we didn't do this for a specific function at a specific point. We did this for an arbitrary function for an arbitrary point. This must always be true. Okay? So that turns out to be a really, really big property for the gradient. Normal to the level curve. So let's write that down. The gradient vector is perpendicular to the level curve. So this is one of the big important properties for gradients, that it's perpendicular to a level curve. Okay? So let's do several contour plots. Let's try to include 1.5 here. What's 1.5? Yeah. What happens when you put 1.5 into this function is what I'm saying. That looks a little bit more complicated. All right, let's actually, I want to actually do this right. Uh, 1.74, let's say 1.75. So I want to include, let's go from 0. How am I going to include 1.75 here? 1.75. 0.25 steps? So if I do 0.25 and I want to, how many contours do I want? 0 to get to 4. 4 would just be 1. 8 would be 2. Let's go 8. So it's the second to last contour that we're going to be looking at. Oops. So 1.5 would be one point five would be somewhere over here. So if I was going to choose my gradient, I guess I have a couple of choices, right? My gradient goes this way or it goes this way. It has to only go one way. How do we know which way it's going to go? The what? Yeah, negative or positive, right? One of us is going to have negative or positive. Do you guys remember which one's negative or positive? Positive was going towards the origin. So, which one should the gradient be? The gradient? So in this case, I think the gradient would be going this way. Out of the two possibilities that we had, it would be going this way. Do you remember what the gradient was for this function at that point?
Two negative numbers. That's, I thought it was negative 408.
Negative 0.4. Negative 0.4. So that's a gradient. Okay? So a gradient is perpendicular to a level curve. That's an important fact. Let's take a look at the gradient again. This time let's take a look at the directional derivative. And let me draw another.
Wait, sorry. So when you look at R prime of T for the level curve, I only see like one tangent line.
Well, it would be, this is the tangent line, so the tangent vector would be going in one direction or the other. Okay? All right. Let's see if we can squeeze in another important property for the gradient. This is the formula for the directional derivative, right? The gradient, whatever it is some fixed vector. We know it's going to be perpendicular to a level curve. And then u is just the direction of some sort. Right? Now, this is a weird way to do this we were just talking about maximizing something earlier. Let's maximize the directional derivative. So let's maximize the directional derivative. And the way we do that is by changing the unit vector around. So let's take a look at the unit vector and see how it would look like in many different positions. Yeah?
Wouldn't it just be the dot product is maximum, which is when cosine theta is maximum?
When is the cosine theta maximum?
At 0
So what she said was that if we're going to try to maximize a directional derivative, we're going to try to maximize this dot product. If we're going to try to maximize this dot product, we're trying to maximize this quantity. The gradient of f is fixed, so the magnitude of the gradient of x is going to be fixed. We're not going to be able to change that. We're moving u around to change things. Wait, what's the magnitude of u? This is a unit vector, so the magnitude of u is 1. And so what's left to look at is the angle between the u vector and the gradient vector. So maximum value for the cosine of theta happens when what? Is when cosine of 0 or theta is equal to 0. So cosine of 0 is equal to 1, and that's the maximum value for the cosine. And theta is equal to 0 would maximize this whole quantity. So they're parallel. So it turns out to find your maximum, the gradient has the direction has to be pointing in the same direction as the gradient. So in not so many words, what we've just shown is that the gradient is the direction of maximum increase. That's the second important fact about the gradient. 1, it's perpendicular to the level curve. 2, it's the direction of maximum increase. Then it would be the direction of, what if theta was equal to pi? So if theta was equal to pi, it's the direction of maximum decrease. Okay? So you're on that mountain, back to the mountain. You want to feel the maximum increase. You want to go up the highest. You're going to go in the direction of the gradient. Okay? If you're water, and you're on a mountain, you want to flow down the mountain the fastest way, right? You're going to go opposite of the gradient to feel the maximum decrease. You know those river flow maps, right? If you draw them on level curves, you'll see a couple of things. You'll see that those river flowing, it's always going to be perpendicular to the contour curves, and it's going to be going in a direction of the fastest decrease, because that's where the water tends to go. Wow, this is pretty deep. Yeah?
On the picture you have of the surface, you draw with the gradient vector.
This surface? Where's my gradient vector? So where am I going to draw it? Up on the surface or down on the ground? How many dimensions is my gradient vector? My gradient vector is a 2-dimensional vector. So it's down here. Does it go inward or outward? Why? Because that's when you go up, right? Gradient. It's a lot to think about. I encourage you to think outside of class. I know you guys do physics and all that stuff outside of class, and you don't ever spend time doing math, but think about, I'm sorry, I was just kidding. Think about how this thing formulates in 2 dimensions with a mountain. Think about how the gradient goes in a mountain, and think about that fly example that we have, right? That fly is flying around. If for some reason the fly is attracted to heat, which way is it going to go? It's going to go towards the heat, right? That is the direction of the gradient. Okay? All right. See you guys tomorrow. Oh, you want your test?
Yes.